Okay. So I really want to say in advance that this is all really very much work in progress, and any kind of feedback is most welcome. I'm still working on all of this. So yeah, my talk will be on the role of mathematics in science, and I will spend the first part of the talk discussing what kind of question we might even be asking if we ask about the role of mathematics in science. There seems to be several things we might be wondering about, and not all seem equally fruitful to me. And then I will talk about my methodology and present one case study that I hope will help me to gain more understanding in this. So first, sorry. Yeah. So why might we even think there is anything to be surprised about if we think of the role of mathematics in science? So here's a way of motivating the question first, which comes from Christopher Pincock. So he says, imagine you're a scientist and the country you perceive as your enemy country has just developed this amazing rocket, and you think, oh my God, we need a rocket as well in order to defend our country and threaten the other country. So you start with this really very practical, even political issue. And he says, well, what you do as a scientist is, or as a physicist, you move to mathematics, you write down some equations like those, maybe those he suggests here. You do mathematical derivations and you end up with some claim, which you then take and you go back to the actual rocket system in order, and you use that claim you derived in mathematics to build a better rocket. And he says, isn't this weird that we start off with something so material and practical and we use something formal to solve the problem? It seems like we just switch worlds. Why is this working? And he says that in this case, we use the formal account, the mathematics, as a surrogate for the real system. So this is the kind of problem maybe you can keep in mind when I discuss specific questions we can now ask about this. Before getting into this, I first would like to outline my methodology, because there are many ways of doing philosophy of science. So my basic goal is to stay close to science as an activity done by scientists. Now, how can we do that? So one thing I aim to do is to avoid simplifications. Scientific work is complex. It involves experiments, mathematics, theory, measurement, social structures, and so on. It involves many things, and I aim to take that complexity into account. It will become clearer later what that might mean. And the second is to avoid speculative philosophical assumptions. There are many philosophical issues about science which are a matter of debate, of course, like scientific realism, mathematical realism, reductionism, and so on. And I aim to avoid assuming position in these debates. So the motivation for that is if we start with a very rigid philosophical framework and then discuss science within that framework, there is the danger, I think, so to speak, trying to squeeze science into that framework, and then we notice we need to distort science and make simplifications which are maybe inappropriate, and it's better not to start with such a very rigid philosophical framework. At least that's what I try to do. So now I said what I do not want to do. What do I want to do? Well, that would be something like integrated history and philosophy of science, which can mean to try and understand, present, and discuss historical episodes in detail without too many simplifications and without presupposing too much philosophical framing. Of course, this can't be completely avoided, but we can try. And then look for abstract concepts and philosophical frameworks that lead to a better understanding of the episodes. Now, what is the problem of the role of mathematics in science? It's weird, I can't see all my slides because of Zoom. Well, it's okay. So one question is, what explains the fit between the realm of mathematics and the realm of physical reality? The idea here is that there are such two realms, and because they fit, we can use mathematics to make claims about reality. I am a bit unhappy about this question because I think, well, if we assume there are two metaphysically distinct realms, That's quite speculative, maybe there aren't. And it seems to be a simplification to say that mathematics and reality fit all by themselves, as it were. There are people in science, of course, that establish fits, and the physical target systems like the rocket are often constructed. So there's not just a fit, it is made in many cases. Another question might be, in virtue of what does a mathematical account represent a target system? So now we assume that it's the representational role that explains the usefulness of the mathematics. Again, I think there are simplifications involved here, namely, first, we seem to assume mathematics either only or basically has a representational function, but maybe functions like conceptual development, calibration, explanation, maybe they can't be explained in terms of representation. I think we shouldn't assume this from the outset. Also, it's a simplification to think that it's pure mathematics that represents and not physical theory, because at first sight, well, we use theoretical physics in the case of the rocket, for example, and not mathematics, not pure mathematics. A third question, what about mathematics explains its applicability? So here we think that it is maybe a property of mathematics that makes it useful for us. That has been asked by some people in the debates as well. But I think, well, why would understanding mathematics be enough, like the understanding the nature of mathematics be enough? Scientists need to come up with theories, experiments, and measurements in order to apply mathematics. So it's not enough to just get the mathematics right. So I'm a bit unhappy with these ways of asking the question. Here is a different way of approaching the issue. It focuses on quantity terms like distance and time, velocity, and so on. And the question is, how are quantity terms, which are defined within mathematics, made empirically meaningful by coordination with measurements? This is, in the coordination debate, this is one way of putting the question. I think this is quite a good question. However, well, sometimes a quantity term can be empirically meaningful, but it cannot be measured. That happens, I think, quite often when we introduce a new term, like when velocity was first used, there was no measurement of velocity. So it's not just measurement that makes the terms meaningful empirically. And also we can start with an empirically meaningful term and make it mathematized. So I think a symmetrical question makes more sense, which is why I choose the question, how come there are successful scientific terms that are meaningful in both mathematical and material environments? And maybe in order to illustrate the shift in looking at the issue, I made two drawings. So in the first case, which corresponds to the slides on the last slide, we think of the scientist as someone who considers mathematics and physical reality and a relation between the two, maybe a relation of fit or of representation or applicability. And the scientist makes use of the relation in order to do science successfully. And I think maybe that's not the best view, and rather I suggest this one, in which we think of the scientist as someone who uses mathematical things like diagrams in the one hand and material things like a screwdriver in the other hand, deals with both environments and uses words that are meaningful in both environments. Like energy, for example, you can calculate an energy, you can depict it in a diagram, but you can also change an energy with a screwdriver or measure an energy. So that is the picture. Now I ask the question, how come, which is somewhat vague, but one way of understanding this question, how come, is to understand it as a historical question. So how did it actually come about that there are successful scientific terms that are meaningful in both environments? And this way of thinking of the question allows me to add a historical case study and to try and learn from the history of science, what the role of mathematics is. And the case study I decided for is a study of velocity. So I want to investigate the development of the meaning of velocity. Now, how do we investigate the meaning of a term? There's a lot that could be said about this, but at least I think it's fair to say that the meaning of a term is closely connected to its use in some sense. So at least it's fair to say that if you use the term velocity in a completely false way, like maybe you want to use a thermometer to measure velocity, you haven't understood what it means. So I tried to find out how the term was used in both mathematical and material environments, and I tried to trace that history. Now, it's not enough to have the term as meaningful in these environments, it also needs to be successful in some sense. And there are many ways of setting up a success criterion for scientific research. And in this case, I decided to just take this surrogative reasoning, which I introduced at the very beginning with the rocket case. So I wanted to find cases in which a mathematical account that makes use of mathematized velocity was used as a surrogate for a material system, and that made testable, correct claims about that system. And with that, the leading question of the case study becomes, how did the concept velocity develop until the mathematics connected to it became useful in the testable surrogative reasoning sense? Here is a table that shows quite a long time span of the development of the term velocity. I will just try to highlight a few features that seem interesting to me. So the mathematization of the term velocity happened in the Middle Ages, in particular in the 14th century in Oxford and Paris. And Galileo and others used essentially that kind of mathematics in the physics they did. But then the term was further developed mathematically. Importantly, velocity could be understood as a ratio of distance to time, thanks to the work of Descartes, and the calculus famously is due to Newton and Leibniz. And in the 18th century, Euler and others added an expression of laws of motion with equations instead of proportions, which was used earlier. So those are some of the mathematical developments. On the material side, I found it interesting to find out that while in the Middle Ages they did this amazing mathematization of the term, they didn't even try to do any experiments or measurements. So there was nothing of that kind apparently. And this only started with Galileo and others in the 17th century. So Galileo connected this mathematized velocity to experiments. And in that time, people already tried to make the term useful in the theory of ballistics so that it could be useful in gunnery. But as I understand it, this only became successful in the 18th century, which is why I traced this very long history. Now to the success criteria that I was mentioning earlier. So when did the term become successful in the sense that I am looking for? For that, I need to distinguish two ways of understanding surrogative reasoning now. So in the first, which I call the weak kind of surrogative reasoning, we would reason within a formal account and then build a material system to test our claims. I call this weak because, well, in this case, we build something that would fit the mathematics. We make a material system in order to test the formal account. So it's a bit less surprising that this works. It's still really cool. And the case I'm going to talk about is pretty amazing. It's by Galileo. It's really well done. But it's not like the rocket case in which you start with a practical problem, which you then solve thanks to a formal account. So this is the case I found in Galileo's work. Just briefly, you imagine you drop some ball for some distance, and then it is deflected into the horizontal, and then it will fall in the form of a parabola. Galileo gives them a geometrical proof of this situation, and he shows that specific geometrical relations are fulfilled when you actually let it all drop like this. And in his proof, he makes use of mathematized velocity, meaning of the geometrical treatment of velocity. But I will not give you the proof now. And there is evidence that Galileo also made the corresponding experiment. That's what you can see on the right. So it looks like he actually did build the system. He dropped a ball. He measured the range of shot depending on the sublimity, as they call it. And his experimental data corresponded with his theoretical prediction. So I think this is a case of surrogative reasoning, but I call it weak because, of course, there's no independent reason for building the system if you don't want to test the theory. In the strong sense, we would start with a practical problem and solve it with the help of a formal account. That's what happened with the Rocket and Pincock's case. And historically, the first case I found really convincing was in ballistics, in gunnery in the 18th century. So, like I said, already in the 16th century, people tried to make a theory of ballistics useful for dealing with cannons on the battlefield, that is useful for the aim of killing lots of people and destroying buildings. But this only really worked out quite late. And important steps in that development were, of course, the theory of motion by Newton, Bernoulli, and others. But importantly, Benjamin Robbins built this thing here, this measurement method, the ballistic pendulum, which was used to measure the velocity of the cannonball as it leaves the cannon, and also the air resistance of this motion. And also, it was important that Leonhard Euler developed numerical solutions of differential equations. So the theory of proportions, or the mathematics of proportions, was not used so much anymore, and instead they used equations the way we do it today. So yeah, this is why I discussed this very, very long time span from the 14th century to the 18th century, because while the term was mathematized in the 14th century, it became useful in strong surrogative reasoning only in the 18th century. To my knowledge, obviously, I'm not a historian, but this is how I understand the history. Now I want to briefly mention some lessons we might draw from this case study. So I asked, how come there are successful scientific terms like velocity, which are meaningful in both mathematical and material environments? And some possible answers are, well, that is because people developed the term such that it would be useful for certain purposes like gunnery and understanding specific kinds of motions. It's because many people did many different kinds of work like mathematics, a geometrical treatment of motion, experiments, measurements, also instrument building, of course, and so on. It's because mathematical and material insights had a mutual influence, and because unfruitful meaning components were abandoned. So for example, velocity was long seen as a property of a completed motion. That's how Aristotle introduced it, and that's how Galileo used it. But later it became seen as instantaneous velocity. So that's how we understand it today as well. And I think that the old meaning was not proven to be false somehow. They didn't argue against it. I think they just switched to a new understanding because it proved more fruitful. And finally, constraints are respected. So there are constraints within a certain kind of mathematics you might use. For example, Galileo couldn't take the ratio of distance and time, like I said before, and that's a mathematical constraint. And also, for example, you can't shoot a cannonball in a straight line, which would be a material constraint. You can't just do whatever you like with a concept. You need to respect constraints from the environments in which you use it. Now the question is what to do with these lessons. Now I plan to go on and think again about how to frame the whole problem. So at the beginning, I said, there are all these simplifications and maybe speculative claims about science that I don't want to make from the outset. But now with more understanding of this historical case, I can go back and ask whether maybe in hindsight, those are fruitful simplifications or maybe harmful simplifications. And I could think more about the philosophical framing of the whole problem and try and find a philosophical framework in which the role of mathematics in science, at least in physics, to be honest, appears as particularly well fitting. So look for a framework that works well with the scientific example. But I haven't done that yet, so I can't tell you about it. And so here is where I end. So this is the references I use in the talk. And with that, I want to thank you very much for your attention.